I am Jeroen van Meij, and welcome to my lecture series on computer and network security. In this fourth video on asymmetric encryption, I will zoom in on some popular attacks that can be performed against the RSA algorithm. There are actually four main types of attacks against RSA. The first one is a brute force attack, which can be used against any type of security algorithm, where the attacker will try all possible private keys D until he finds a valid one. Second type is the mathematical attack, where the attacker will take n and try to factor it into 2 primes p and q, knowing that n equals p times q. Third one is a timing attack. Here the attacker will exploit knowledge on the modular exponentiation algorithm, where the number of multiplications performed by this algorithm depend on the number of 1 bits in the exponent. For decryption, this is the value of d. If the attacker can derive the number of multiplications from the total time the algorithm takes, he can derive the number of 1 bits in d and will have an easier time determining d. Finally, the fourth one is a chosen ciphertext attack, where the attacker will exploit some specific properties of the RSA algorithm. Let's start with the security of RSA versus brute force attacks. Currently, RSA is considered secure as long as the size of n in bits is large enough. In the table here, you can see how we can relate the size of n in number of bits to sizes of keys in different types of algorithms. So in the first column, you see the size of the key in bits using symmetric encryption. Second column, you see the size of the public and private key using Diffie-Hellman, which we will talk about in another lecture. Third column is the size in bits of n of RSA. And finally, the fourth column, you see the modulus size in bits in elliptic curve cryptography, which is a modern version of asymmetric encryption. Currently, the three last rows are considered secure up to at least 2030, because as time goes on, computational power increases and thus it becomes easier to perform brute force attacks. As you can see, a large number of bits are needed to keep RSA secure compared to symmetric encryption. For symmetric encryption, for example, a 128-bit key takes about the same time to brute force as an RSA value of n with 3072 bits. Elliptic curve cryptography takes less bits to be secure, which is an advantage. And let's take a look at the second type of attack, the mathematical attack. There are three approaches that have been identified for mathematical attacks against RSA. The first one is to factor n into the 2 primes p and q. Second one is to determine the totient of n directly without first trying to find p and q. And the third one is to determine the private key d without finding the totient of n. The first two have been shown to be mathematically equivalent, so the difficulty of factoring n into 2 primes or determining the totient of n given n are equally difficult. The third one, directly determining d without first finding the totient of n, is considered more difficult, so an attacker would go for one of the first two approaches. Finding the prime factors of a very large number n is considered a computationally hard problem. However, as computational power increased throughout the years, also this factoring problem became easier to solve. Here you see a table when RSA ciphers with a certain number of decimal digits for the number n were broken. Originally, in 1977, the three inventors of RSA dared Scientific American readers to decode a cipher which was using a value of n with 129 decimal digits or 428 bits. They predicted that it would take up to 40 quadrillion years before the cipher was broken. However, as computational power increased, a team already broke the cipher in April 1994. In the meantime, also RSA laboratories had launched different challenges with a value of n with 100 digits, 110, 120, 130, and so on. Also, all of these were broken. Most recently, in 2009, researchers broke an RSA cipher using an value of n with 232 digits, or 768 bits. This shows that a very large n is needed for RSA to be secure. Traditionally, something called a quadratic sieve was used to factor n into primes. However, more recently, a newer algorithm was developed called a generalized number field sieve. This algorithm is able to factor very large numbers in only 20% of the computational effort of the quadratic sieve, as such helping to break RSA ciphers. As such, there are two threats when it comes to mathematical attacks against RSA. The first one is the continuously improving computational power, which allows factoring larger and larger numbers into primes. The second one is the refinement of the factoring algorithms, which become more efficient over time. And here you see a comparison between the general number field sieve and the special number field sieve in terms of how long it would take to factor a certain number with a certain number of bits in terms of number of MIPS years. And you see this more efficient algorithm takes way less time to factor a number with the same number of bits. There are some safety precautions that can be taken to make it harder to factor the number n. First, P and Q should have nearly the same number of digits. If one of the two is much smaller than the other, it becomes easier to factor n. Both P-1 and Q-1 should contain a large prime factor, again making these algorithms harder to execute. Also, the greatest common divisor of P-1 and Q-1 should be small, which also makes it harder to find P and Q. Third type of attack is a timing attack, where the snooper will determine the private key by keeping track of how long it takes to decipher a message. This type of attack can be used against all public key encryption algorithms, and it is a ciphertext only attack. As such, it doesn't require the attacker to obtain any plain texts. For RSA, it makes use of the timings in the modular exponentiation algorithm, because as I mentioned, this algorithm will take longer or shorter depending on the number of 1 bits in the exponent d. Based on the timing, the attacker can then derive how many 1 bits are in d, and based on that can estimate the value of d. There are different countermeasures against this type of timing attack. The first one is to make sure that the exponentiation always takes the same amount of time. For example, by performing some dummy calculations if the algorithm executes faster. However, this obviously degrades performance. Second one is adding a random delay, where the delay is not fixed until a certain total time, but is some random value between a minimum and a maximum. This results in some better performance, but still adds additional calculation time that is unneeded. So, the third type of countermeasure is to use blinding, which multiplies a ciphertext by a random number before decryption. As the attacker does not know this random number, he is therefore not able to derive information about d from the timing of the modular exponentiation. And let's take a closer look at how blinding can be implemented to overcome timing attacks. Normally, during decryption, this operation is performed. So we calculate ciphertext to the power d modulo n to retrieve our plaintext m. However, instead of directly calculating the plaintext, we replace it with this procedure consisting of 4 steps. First, we generate a random number. This number does not have to be known to the sender, only to the receiver of the message that will decrypt it. This number should be between 0 and n-1. Then we multiply our ciphertext C with this number r to the power e. E is the public key, so it is known to the receiver of the message, and take modulo n. Then we decrypt this new message C dash using the normal RSA procedure by calculating C dash to the power d modulo n. Then in the fourth and final step, we can actually retrieve our m by multiplying m dash with r to the power -1 modulo n. As an attacker can only intercept C but not C dash, as the attacker does not know r, based on the timing of this operation, the attacker will no longer be able to derive useful information, as the attacker should know C to be able to derive this information. We can prove that this operation indeed gives us m by using the fact that r to the power ed equals r modulo n. I invite you to try to calculate this on your own. It has also been shown that blinding results in a small performance penalty of 2 to 10%. However, this is much smaller than the penalty from using a fixed time or a random delay when performing modular exponentiation. As such, most modern implementations of RSA include this blinding to avoid timing attacks. The fourth and last type of attack is a chosen ciphertext attack, or CCA. Here the attacker is able to give some ciphertext to a receiver and receive back the corresponding plaintext. The attacker can choose blocks of data that yield additional information useful for cryptanalysis. Let me give you an example of how a chosen ciphertext attack, or CCA, can be performed. This attack relies on the property that the encrypted version of a message M1 multiplied by the encrypted version of a message M2 equals the encrypted version of a message M1 times M2 with the same key, PU. Now, let's assume we are given some ciphertext message C, which equals m to the power e modulo n, that the attacker has obtained. The attacker knows C, but doesn't know m. Since the attacker doesn't know the private key D, he is not able to derive m either. However, he can obtain m using a chosen ciphertext attack. First, the attacker will compute x by multiplying C with 2 to the power e modulo n. Since e and n are part of the public key, the attacker can find out what are these values. The attacker then submits this chosen ciphertext x to the receiver and receives back the decrypted message y. Y equals x to the power d modulo n. Even if the attacker doesn't know d, by submitting it for decryption, he can know at least the associated plaintext y. Now we know that x equals c modulo n times 2 to the e modulo n. C equals m power to the power e, so we can then derive that x equals 2 times m to the power e modulo n. Since the attacker knows that y equals x to the power d modulo n, we now know that y equals 2 to the m to the power 2 times m to the power e to the power d modulo n, or y equals 2 times m modulo n. From this formula, the attacker can easily derive what is m given y. However, this equation here no longer holds if we add some random padding to m before encryption. And that is the way to counter this chosen ciphertext attack. To avoid this type of CCA, as well as more elaborate chosen ciphertext attacks, it is advised to pad your plain text when using RSA encryption. And the way it is advised is by using optimal asymmetric encryption padding, or OAEP. And here is how it works. We take our plain text message block M and some optional parameters P and a randomly generated seed. We use a hash function to create a hash of these optional parameters. We add 0 padding up to a certain length and then concatenate M, which results in our data block, or DB. The seed is sent through a hash function called the mask generation hash function. So it becomes the same length as DB, and the two are XORed, exclusive ORed, into the masked DB value. The masked DB value is also sent through this mask generation hash function and XORed with the seed to create the masked seed. The masked seed and the masked data block are then combined into EM. EM is then the final data block that is used as input to RSA. By using this procedure, it's no longer possible to execute chosen ciphertext attacks. Moreover, by including the masked seed into EM, the receiver is able to retrieve the seed value and then decrypt the message, as the XOR operation is invertible.